But that what we proved the last time was that r hat can be written as e to the omega, and omega is in fact anti-symmetric. Okay? So that's what we proved the last time. It's an if and only if statement, which means it is a rotation matrix. Then the exponent has to be anti-symmetric. And if the exponent is anti-symmetric, then this guy is anti-symmetric. Then that guy is r hat is a rotation matrix. Yeah, why does it look so dark? It's a little bit strange, no? It's okay. You guys can see, right? Okay. What we are writing down over here involving omegas is just the statement that omega needs to be antisymmetric. So, and because the space of antisymmetric matrices forms a vector space, you basically to write down the most general real antisymmetric matrix, you enumerate all the basis matrices and sum over them, right? So the most general antisymmetric matrix is just the sum over the basis, the superposition over all the bases. And this is what's going on here. And just a reminder, as an example, in 2D, yeah, every time I teach, you're going to hear me complain about markers. So, in 2D, as we have seen, I times j hat. There's only one generator in 2D because there's only one way to rotate. Okay, it's just rotating about the one. You're rotating the 1-2 plane. This is in fact given by, represented by the Navier-Civita matrix, right? So if I don't put indices, because there's only one, so I don't put indices on this guy, and therefore there's no indices in this. This is a matrix, right? And so is this guy. And in 3D, we also enumerated the antisymmetric matrices, right? The first one, I, j hat 1, 2, is 0 on the diagonals. Remember, it's antisymmetric. So it has to be 0 on the diagonals because it's antisymmetric. And then, because it's antisymmetric, all you need to do is look at the off-diagonal components and put a 1 for each of the independent basis generator. So this guy is 1, this will have to be -1, and then you put a 0 everywhere else. Then you do j hat 2, 3, 1, 3, then this will be 0, 0, 0, 0. 1, 3 means the first row and the first column. This will be -1, 0, 0, 0. Okay, and then I, j hat 2, 3, 1, 2, 1, 3, and then 2, 3. This will be 0, 0, 0, 0, 0, and this will be 1, -1, 0, 0. Okay, and that's it, because there are only 3 components, off-diagonal components, and that's the most general thing you can do. And so the most general 3-dimensional rotation matrix written in this way is minus I omega 1, 2 j hat 1, 2 plus omega 1, 3 j hat 1, 3 plus omega 2, 3 j hat 2, 3. And that's the most, where all the omegas are real. this is in fact the most general rotation matrix. Okay? And so it's also good to remember what they mean. If you remember how the it comes down to remembering how the two-dimensional case works, right? So remember that in terms of matrices, this guy is 0, 1, minus 1, 0. And you see that everybody actually has the same structure. There's 0 almost everywhere except 1 minus 1, 1 minus 1, 1 minus 1. So what it tells you is that this guy rotates the 1, 2 plane. Right? This is what this means. Or it generates, it itself doesn't rotate 1, 2 plane, but it generates the rotation of the 1, 2 plane. So you can basically read off, because the zeros means it's basically not touching anybody else except the row and the column that it corresponds to. So what it means is, for example, J hat 1, 2 will generate a rotation for the 1, 2 plane, because it's exactly the same thing here. All these are zeros, so you'll find that it doesn't touch. It's exactly this case here. So this guy is 1 and 3, 1, 3, and 3, 1. So this guy rotates, generates the rotation of the 1, 3 plane, and this guy generates the rotations around the 2, 3 plane, right? So this is something important to remember. Rotations really involve planes, 2D planes. Okay, this is the most fundamental definition. There are special cases where you are you have a different interpretation to how rotations work, and in fact, the three-dimensional case is one example. But the most general way to think about rotations is that you basically pick a plane and you try to rotate it. Doesn't matter how many dimensions you're in. You pick a plane and you rotate it. This set of bases illustrate that very well. In other words, if you just pick one of them and you just exponentiate it, you'll find that that's exactly what happens. So for example, let's just make it very clear. For example, if you write down e to the minus I, theta j, let's pick for example this guy here, j hat 1, 3, you would find that this guy, because it only rotates the 1, 3 plane, so it will not touch the 2 plane. The 2 plane is the guy in the middle, so it will be 1. And then the 1, 3 plane will be cosine theta minus sine theta, right? So we've written it as 1 minus 1. You'll realize that generates a counterclockwise rotation for a positive angle. If you put minus 1, 1, then for a positive angle, it will generate a clockwise rotation. So it's sort of a convention, but you have to work it out to see it for yourself. So this will be cosine theta, 0, 0, 0, 0. Okay? So this is what I mean, that rotations involve 2D planes, and this basis is not a unique basis. Obviously, you can choose a different basis, but this basis shows very clearly that rotations are in fact just basically a choice of a plane and then rotate it. Okay. Now, the other thing I wanted to say, which is mainly convention, is that because my definition is that omega is anti-symmetric, you will find that the j's are also anti-symmetric in this label. So if you allow both, if j hat AB is also anti-symmetric, then you find that the superposition here is equals to what you see over here. See here, I don't have a 1 over 2, but I have a 1 over 2 here. And the reason is because omega 1, 2, j hat 1, 2, for example, what is that equals to? This is equals to 1/2 omega 1, 2, j hat 1, 2 plus 1/2 omega 2, 1, j hat 2, 1. Okay, so let me just put it as a note. Because this is anti-symmetric and this is anti-symmetric, so I can swap this 1 and 2, and I can swap this 1 and 2. Swapping 1 and 2 will cost me a minus sign over here, and cost me a minus sign over here as well, but then they will cancel out. The minus signs will cancel out. They will combine into just 1, right? So that's why this guy here is the same as this guy here, except that of course this is a three-dimensional case, and this is the general case. Okay. So there is a way to write this this set of bases, and let me do it here. So I times j hat AB in my notes I put ij AB. So this is the A B component of the ij antisymmetric basis matrix. Okay, so don't be confused by the indices. This is a label for which antisymmetric basis you're referring to, and AB is the component of it, the row, the A row and the B column. And if you check, you can see that this is equals to Kronecker I, Kronecker J, AB, antisymmetrized. And either antisymmetrized AB or antisymmetrized AIJ is the same thing, because we realize it's equals to the following. It's just minus JI. Okay, you can check. How do you know whether it's correct? You can just check. Just plug in IJ for say 1, 2, and then you run over AB, and you realize that you will recover this matrix, for example. If you try to plug in 1, 3, and then run over AB, you will realize you get this guy, right? And then with some experience, you will be able to argue more generally that this guy will only, as you run for a fixed pair of IJ, when you run over AB, you discover that this matrix is 0 everywhere unless AB equals to IJ, or AB equals to JI. Okay, that's the only two possibilities. Yeah, so let me just write down 0 unless AB equals to IJ or JI. Okay, and in fact, when AB is IJ, you get 1, And when AB equals to JI, you get minus 1. So why is that all important? It's important because we're about to promote. This is the rotation matrix acting on a real vector, right? But what we're going to, why this is important is we're about to promote. We're going to promote the rotation operator to a linear operator acting on our Hilbert space. Okay, and so and remember, the reason is because we want to find a way to implement rotations on our Hilbert space, right? When you rotate actual space, what does that mean in terms of the quantum mechanical system? It means that you also need to find a way to act the rotation on the Hilbert space. So there needs to be a way to implement that through a linear operator, right? So in other words, you need to do d of r hat on some cat in your Hilbert space, right? And of course, what that means is that you're going to have to find a way to write down the linear operator in terms of now the same rotation angles. Okay, the same rotation angles because that's what you use to describe your rotations. So these are the same rotations, but now J is no longer a matrix. These guys are now operators. Okay, they're now operators acting on your Hilbert space. And we're going to figure out what are the algebraic properties, right? So in order to preserve the multiplication groups, we need to make sure that the JAB obey same rules as J hat AB, J hat LM. In other words, if you remember, we said that the product of group elements like that is completely determined by the commutators of the generators, right? So this is the Baker, Campbell, Hausdorff lemma, that when you multiply group elements together, the exponents don't add, but they don't add the difference between multiplying complex numbers, exponential of complex numbers, and exponential of operators or matrices, is that the exponents add plus there are commutators that show up. And in other words, if you want to know how to multiply exponentials of operators, the key point is to understand how they commute, right? What is their commutators? So, because the commutators determine completely their multiplication rules. So therefore, you need to know how do they commute? What are their commutator structures? And so this is why we need to know this guy. Okay, so once you have a parametrization for these guys, you can go ahead and work out what this commutator are. What this commutator is. And then you can immediately promote it to this operator. So let me just write it down because I think this is your homework problem. So this is the Lie algebra of SOD. So remember, S means is unit determinant, O just means it's orthogonal, and because it works for any dimension, so I may as well tell you what it is. Right? This is not, although we're going to be doing mainly 3 dimensions, doesn't hurt. Doesn't hurt to know what the d-dimensional result is. Okay. So let me write that down. But first, of course, I have to find it. Where the heck is mine? There we go. So J, KL, commuted with J and N, turns out to be equals to minus I. And then connector K, J, L, and then you anti-symmetrize NN. So remember, this square bracket means you write down NN, and then minus NN. Okay? So there are actually 2 terms in this. Minus connector L and N, J, K. K, L, L, K, yes. Okay, again, this follows from here. And like I said, you have to promote the Lie algebra for the matrices to the Lie algebra for the operators because you want them to have the same multiplication rules. Okay? But even though one is a matrix and one is an operator, right? So they're fundamentally different objects, but they need to be the same, they need to obey the same rule. Okay, so this will guarantee, so let me just make it clear. So this guarantees that when you multiply the representation of one rotation matrix with the representation of the another rotation matrix, this will give you D of R hat 1 times R hat 2. Okay, so what this means is that you give me a rotation matrix, I will convert it into a linear operator. Give me another rotation matrix, I'll give you another linear operator. When I multiply the 2 linear operators, what will it give me? It will give me multiplying the 2 rotation matrices together first, and then converting it to the corresponding linear operator. Right? It has to do this, otherwise it will not obey, it will not preserve the structure of the rotation group. Right? It needs to do this. Now, and if you impose this Lie algebra, then you're guaranteed that this is true. Okay? Okay, so before we go on, are there any questions for me? No. Everybody is quiet. I know it's Monday. Monday and Friday, right, are the days where people are very quiet. Friday, you want to go home, right? And then Monday, you just came from home. So, okay. So, before we go on, I want to emphasize an important geometrical aspect of rotations, right? At the level of what is called the metric. Yeah. Yeah. Yes.
MJN.
MJN. This one?
Yes. Yes.
Oh, we have 4 indices, right? So for example, this guy, I'll just write it up for the person. It means Kronecker KM JNL. That's the first term. And then I'm supposed to swap M and N and put a minus sign. So I put minus Kronecker KN JNL. Okay. And so then this guy also has something like that, right? So altogether there are 4 terms when I write this down. The reason why I do this is because it makes it clear that the symmetry of the indices match up on both sides, right? So it has to be anti-symmetric in KL because you discover that this guy is anti-symmetric in KL. So maybe I should write this down. You will discover that from here that J hat Ij is equal to minus J hat Ji. Okay, I didn't have to impose it by hand. Just from this alone, you can prove that Jij is equal to minus Jji. Okay, but when I promote it to an operator, this will preserve the structure of these indices. Okay, so if I write it this way, then it's clear that it's anti-symmetric in NN, right? Because there's an anti-symmetry on the NN and on the NN. But then you notice the difference between this term and this term is that I took KL and I swapped KL also with a minus sign, right? So it's both anti-symmetric with respect to KL and NN, which means that both sides are sort of manifestly, as they like to say, manifestly antisymmetric in both KL and N. Okay, and that's why I write it the way you write it. But if you want to write it out explicitly, there will be 4 terms in total. Okay. Good. Okay, so maybe I don't do the metric right now. Let me talk about the metric in a little bit. When I write down the Laplacian, I'll tell you guys about the metric. Let me, in fact, do one more thing about what we were just doing here. which is the change of when you try to sandwich a rotation between. But let's see it more generally. I'll do it for the general case, and then we'll do it again for the three-dimensional case, right? Because I'm doing this because I feel it's not well appreciated. At least it's not taught very, very well. That rotations are really rotations of a plane. And then when I do 3D, I'll tell you what's so special about 3D, right? There's a dual picture for 3D that does not exist for other dimensions. But let's calculate this explicitly, okay? So what will happen is that you know that the exponential can be the exponential of an operator. Let's call it something else. Let's call it y. Okay, because x is now our position operator. So this guy. So let's figure out what does that mean to do this. Okay, so this guy, it turns out, is of course r hat times the sum over y to the L over L factorial r hat transpose. So I need a hat on here because I'm now doing the matrix. I'm now doing the matrix version of this, right? So what will happen is that I can write this guy as the following. I can write this as I can bring this guys inside, and I can write it as r hat y, and then I can write r transpose r hat. Why can I do that? Because this is 1. But remember, these are orthogonal. Rotation matrices are orthogonal. So r transpose r is 1, and then I can keep writing it like that, right? So I can keep writing it and r transpose r. And I can do it L times, because this is an L, y hat to the L. So in other words, it must be the same as r hat y hat r hat transpose to the L, okay? Because when I write it out L times, the r hat on the left can be put out. The r hat transpose on the very end can be also put out. But all the r hat transpose times r hat, all of them will cancel out because it will just be 1. Okay? So it will just be that guy. Remember, all of them are 1. Okay? And so that, what does that mean? It means that you can now basically bring in the r hat into the exponent, which is e to the r hat y hat r hat transpose. Okay? And now we can calculate what this is. Because we know something. We know that I j hat AB, let's calculate it. Okay, so R hat, let's calculate what this guy is. Okay, so what is this? This is actually, remember that, let's calculate, for example, what is this? What is the ij component of this? Okay. So what this is r hat, and then the I component, and then it's going to be summed over m I j a b m n r hat transpose n j. Okay. So again, I'm just doing matrix multiplication, but in index notation. right? So, but this is a transpose, so I can write it as R hat IM, R hat JN, dotted into I, J hat AB, MN, okay? And then what is that? This is R hat IM, R hat JN, and this guy is nothing but my Kronecker deltas, Kronecker A, Kronecker B, and N, anti-symmetrized. Okay? And then, remember that I want to, what's going on is that actually all I want to do is I want to figure out what is minus I over 2 omega AB, and then remember these are just numbers, but I want to figure out what is this guy contracted into R hat J AB R transpose, right? This is what I want to figure out, because that is exactly what I was writing over there, is R hat Y R hat transpose, right? This is what I want to figure out. But now, what I have is I over 2, minus I over 2 omega AB, and then now I have this contraction with R hat IM, R hat JN, and then I have Kronecker A, Kronecker B, anti-symmetrized MN. But this guy is contracted with this, so this is actually minus I over 2 omega MN anti-symmetrized. Kronecker RIM RJN. Okay? Because again, AB is contracted with AB, and so you just bring the indices over and you anti-symmetrize it. But then, this is anti-symmetric already, right? So omega MN anti-symmetrized, what is it? This omega MN minus omega NM, but this guy is anti-symmetric, so this is just 2 omega MN, and the 2 will cancel this, and this will just give me minus I omega MN, and let me write it this way, it's actually just R hat IN R hat JN omega MN. Okay? So if you look at this, all that's happening is that when you sandwich the rotation operator between two rotation, between R and R transpose, what it does is that the bases are what is it? The bases are the bases, right? What it actually does is you should think of it as it changes the rotation angles. So let me just do the other calculation just to make it clear. So what am I talking about here? So when I ask, if I don't rotate, okay, what do I get? I get, this is 1 over 2 omega AB IJ hat AB. I'm sorry, AB IJ. This is, of course, just 1 over 2 omega AB, Kronecker A, Kronecker B, IJ, and this is just minus omega IJ. I'm skipping a few steps because we just did it, right? So you just contract AB with AB, you get I omega IJ anti-symmetrized, but because this is anti-symmetric, so you just get omega IJ. So what it's telling you is that essentially what it's telling you is that R hat omega AB IJ hat AB R hat transpose rotates. What it does over here is that it's actually rotating the rotation angles in such a way that you are basically contracting the rotation angles with the rotation indices here. The indices of the rotation angles. Right. So this is actually R hat. I n R hat J n of omega n n. Okay. So let me not put a minus sign here. But I have a 1/2. 1/2. So I don't have a minus sign. So again, compare this calculation, which tells you that this contraction is just giving you omega ij, with the same calculation, but with R and R transpose. Right? With R and R transpose, you see that the difference between these two guys is that this is omega ij, but this is omega ij, but rotated with the two rotation angles, rotation matrices, right? So i.e. omega ij transforms as a rank 2 tensor. Or maybe rank 2 tensor under rotation. Because in other words, this is omega prime. If you define this as omega prime ij, then if you compare between the two, the indices are contracted with the rotation matrix. And that's what a tensor is. A tensor is basically an object with multiple indices, and when you have a well-defined transformation law, the tensor will transform according to the transformation law by contracting all the indices with the law that you are concerned with. In this case, it's the rotation. Right? That's what a tensor is. Okay. Any question? Yes. Yes.
Minus sign.
Minus sign.
The first line.
Oh, thank you. Yeah. Yeah, I didn't want the minus sign. There's a minus sign in the exponent, but I didn't want the minus sign because I just want to emphasize that the exponent involves omega ij, but when you sandwich it between R and R transpose, now you get omega prime ij, which is rotated by the rotation angles. Right? Good. Any other questions? So we should take a break. Let's come back in 10 minutes, okay? So, what are we trying to do here? So, let's talk about 3 dimensions first, okay? Because just in case that the D, maybe I should say one thing because somebody just reminded me. I forgot to say, how many generators are there in D dimensions? Okay, so the way to understand this in some sense, we've already figured out for 2 and 3 dimensions, and that's the most important cases. But it's easy to answer this question because remember the number of generators is related to the way we enumerated this basis, right? So remember that all the diagonals are 0, and the way we denoted enumerated the basis was we figured out that all we have to do is put a 1 in one of the slots in the upper triangular entries, and then the corresponding off diagonal term in the lower triangular part would be -1 and 0 everywhere else. So basically the number of upper triangular or lower triangular, lower triangular or upper triangular entries is in fact equals to the number of generators of independent generators. Okay, and how does that go? So if you're in D dimensions, the total number of entries is D squared. You subtract off the diagonal components because it's all 0, so that's minus D. And then you just divide by 2. Right? That's exactly how many upper or lower triangular entries there are. And so this is just D times D minus 1 over 2. And what you then do is you check, right? Whenever you have a general formula, you should check. So for example, let's check. Let's call this N. When D equals to 2, what happens? N is equals to 2 times 2 minus 1 over 2, and therefore it's just 1. Okay? D equals to 3, N equals to 3 times 3 minus 1 over 2. So this cancels, and you get 3. Right? So it works out. What we have done so far, it works out. And for N equals to D equals to 4, it will be 6, and so on. Right? But we won't continue because we really only need the 2 and 3 dimensional cases. Okay. So now I want to talk about the 3-dimensional case in a little bit more detail because what's going to be important for us is the 3-dimensional case, right? So so we're going to focus on 3D rotations. In 3D, there's something special about 3D because if I choose a plane and I rotate that plane, this is the most, again, this is the most general way to think about rotations. But because we're in 3D, when I choose a plane, there's a unique direction that's orthogonal to that plane, right? So if this is my plane, there's only one direction that is perpendicular to the plane. So let me write it down. Pick a plane. There's only one direction perpendicular to it. Okay, so in 2 dimensions, there's no such thing. If you're in 2 dimensions, there's no orthogonal, there's nothing orthogonal to it, right? If you're in 2 dimensions to talk, there's no orthogonal direction to talk about. If you're in 4 dimensions, if you pick a plane, there are 2 directions, 2 independent directions orthogonal to your plane. So orthogonality is now ambiguous. If you are in even higher dimensions, the higher dimensions you go, the more ambiguous orthogonality would mean to a plane. So 3 dimensions is unique in the sense that there's only one direction to every plane, and therefore, if you specify a plane, you can also specify it by specifying the orthogonal direction, right? So it means specifying a plane. It's the same as specifying the normal. And this is something you guys have probably seen in multivariable calculus, right? So if you give me a plane, okay, then it's the same as saying, okay, let me tell you what the normal is. Okay. It's the same thing. You can describe the plane in equivalent ways. Right? In differential geometry, it's called a dual, and you'll see it in a little bit. So what it means, what it tells you is that it must be possible to describe the generators in a different way. So this rotates. These guys generate rotations on the AB plane. Yeah. So now we discover what are the generators J hat A that generates rotation about the A axis. Because like I said, there are two different ways to talk about rotations in 3 dimensions. Either you specify a plane, the 1-2 plane, or the 1-3 plane, or the 2-3 plane. Or you can say, for example, if this is 1-2 plane, then it's equivalent to saying I'm going to rotate about the third axis. Okay? If I do say 1-3 plane, then I can also say that that's equivalent to rotating about the -2 axis, right? So this is 2, but this is the -2 axis, right? Let me not write it down because I don't want to say it's -2, but it is a -2 axis, right? And if you do it about the 2-3 plane, then this is saying that you're rotating about the 1 axis, right? So let's write it down. So 1-2 corresponds to 3, right? This guy, 1-3 corresponds to, it's a little bit sloppy, but -2. And then this is corresponding to, this is 2-3 plane corresponds to 1. Okay. Maybe a better way to write it is, let's write it in terms of the axis. E3 means a unit vector along the 3 directions. This is now -E2, and then this is E1. I'm using the right-hand rule, right? That's why there's a minus. That's why a minus sign here. So counterclockwise on the 1-2 plane corresponds to a positive angle rotation about the 1 axis, for example. Sorry, about the 3 axis, right, for example. And we'll discover this is exactly what's going to happen. And it doesn't take a lot of work because, so let's look at, for example, rotations using this language that we had earlier, right? So -I/2 omega AB, J hat AB. But now we're in 3 dimensions, so there is an object that can convert two index objects into one index object. And that's, of course, the Levi-Civita symbol. Right? So in 3D, Levi-Civita is 3 index. So I can now define J hat A to be 1/2 epsilon ABC J hat BC. I should also say that I'm doing it for the rotation matrix itself, but all I'm talking about, all this I'm talking about will also carry over for the operator, right? So if I do D of R hat, this will be e to the minus I over 2, the same rotation angles, but now JAB without the hat, meaning this is the operator. Then the same thing would apply. JA would be 1/2 epsilon ABC JBC. Okay? And again, the reason for the 1/2 is because this is anti-symmetric, and Levi-Civita is also fully anti-symmetric, right? So you will discover that the anti-symmetric sum over the anti-symmetric components will cancel out the 1/2. And you will discover also that this implies that you can invert this. JAB, for example, is in fact epsilon ABC JC. For example, J hat 1, 2, what is that? This is epsilon 1, 2, but C has to be distinct from 1, 2. So the only component that's non-zero is 3, so you get J hat 3. And epsilon 1 to 3, if you remember, is 1. So this is just J hat 3. So rotation generator of rotation about the 1, 2 plane is in fact the rotation about the third axis. That is in fact, the Levi-Civita symbol is in fact the way to express this. Okay, so this is what we just discovered by inspection. But mathematically or algebraically, this is how you actually discover it. So for example, J hat 1, 3, what is that? It's actually epsilon 1, 3, and then remember the third component has to be distinct from 1 and 3, so the only possibility is 2. J hat 2. But what is that? This is actually minus epsilon 1, 2, 3, because I have to swap 3 and 2, J hat 2, and so this is minus J hat 2. So again, generator, or the generator that rotates the 1, 3 plane, okay, is in fact equivalent to the rotation, the generator that generates rotation about the negative 2 axis. Okay? So this minus sign even matches up with this minus sign. And then J hat 2, 3 is epsilon 1, 2, 3, 2, 3, 1, J hat 1, and this is equal to epsilon 1, 2, 3, J hat 1, because you just swap you move 2 places to the left, and that doesn't cost you any minus sign, and therefore you get that the generator of rotations on the 2, 3 plane is the same as generator of rotations around the first axis, right? So this is the geometric or the pictorial way to see it. This is the algebraic way to see it, right? So let me just put a parenthesis around here and remind you this is the algebraic realization of those pictures. Okay? Okay, but now we can in fact plug this guy into that and figure out what happens. Okay, so when I have I over 2 omega AB, J hat AB, or hat or without the hat, I can now replace it with I over 2 omega AB epsilon A, B, C, J hat C. Right? This is my definition. So in fact, this can be converted into, if I write omega AB with a 1/2 epsilon ABC, if I define this to be theta C, then you see that this becomes minus I theta C J hat C, or in other words, minus I theta dotted into J. And this might be more familiar. This is now the rotation of, this is rotation now written in terms of the rotation angle and the axis of rotation. Right? And this is what's going on here. So the interpretation is now R hat is now e to the minus I theta dot J, and theta dot J is the rotation, and the length of the rotation is the rotation angle, and theta divided by the length is the rotation axis. Okay. Right. And to see, of course, all you have to do is just refer it back to this. Right? So for example, if theta points in the one direction, when theta points in the one direction, we already know it generates, it gives you rotation on the 2-3 plane, and it's the same as rotating about the one axis. If theta points in the -2 axis, it generates rotation in 1-3 plane, and so on. Right? So that's what the interpretation is. And so likewise, when you promote it to an operator, it's the same thing. All I have to do is just drop the hat. Strictly speaking, I need to put a hat there. Maybe I'll do this, right? So A, okay, and then this one there's no hat, because now this is an operator. Okay, and furthermore, now there's a question of, when I promote this guy to an operator, remember I need to know how to multiply these guys together. When I multiply two different representations of two different rotations, how do I multiply them? And the multiplication rules are determined again by the Lie algebra, right? So usually when we specialize to the Lie algebra of rotations in 3 dimensions, which is SO3, we write that in terms of these guys and not in terms of these guys. Right? It's just easier to write them down, and you see that it's easier because, and I won't derive this. So, now it's time to talk a bit more about the actual linear operators acting on our Hilbert space, right? Because after all, we're doing all this because we're trying to do quantum mechanics. We're not doing geometry for its own sake, but we're trying to understand rotations more deeply so that we can realize, we can implement these rotations on our Hilbert space. So in fact, the first thing to do is to figure out how do we in fact implement it on, for example, the position eigensets. Okay, so let's do it. So now I have a linear operator that's a function of my rotation matrix. And the first thing I want to study is how does it act on my position eigenstates, right? So naturally, so this is a position eigencats. So naturally what I want to do is simply to demand that it will simply rotate my coordinates. Right? So R hat acting on X is just the usual matrix multiplication. But now it's acting not on, these guys themselves are not acting on coordinates, but acting on the position eigencats themselves. So the first thing you can show is that if this is your definition, in fact it's a definition, then this will guarantee what I just said earlier, which is that if you want these linear operators to behave like rotations, the first thing you want them to do is that you want to make sure that they preserve the product root of multiplication. How is that so? Because when you multiply, for example, two rotation linear operators on X, what happens? The first guy will do, let me just call it, let me do it step by step, right? So this will be R2 acting on X, and then this will become R1 acting on R2 acting on X. But that's of course just D of R1, R2, both acting on X. And since the eigencat is arbitrary, is a arbitrary basis vector, therefore this operator must be equal to this operator, which is exactly what we are saying over here. Okay. This is of course, if you are a mathematician, this in fact is what you demand of representations, right? If something is a representation, it must obey or it must preserve the multiplication root of rotations, or any other group that you are talking about. And then for us, what we discover is that rotational symmetry and this is important, rotational symmetry of space implies so let's see it with it. So we've already seen this for translations, if you guys remember. Because space is translationally invariant, at least for infinite space, not the box case, or for periodic domains. Translations is there's translation symmetry in either periodic domains or in infinite flat space. That we have seen implies that the translation operator implemented on the position eigencats gives you a unitary operator. So likewise, we're going to see right now that rotations on infinite space will also give you a symmetry, because whether I do this or this, space is the same, right? There's no way I can distinguish between is this space this way or this way. There's no way I can orient space in a way that I can tell the difference. And that, when you implement it as an operator acting on your eigencaps of position, will translate into the unitary character of D, right? So let's do it. So D, so there I go again, I'm going to complain about markers, right? I talk for 2 minutes and then the markers dry out. So D acting on D acting on X, as we've said, gives you Rx. So therefore D acting on X prime is also R acting on X prime. Okay? And now let's consider the inner product between these guys. Okay, and this is just nothing but the delta function, and now I'm going to work in D dimensions because it doesn't matter what dimensions I'm in. It will be a rotated version of X minus rotated version of X prime. Okay? But I'm rotating everybody in the same way, so this is just rotation, delta function of the rotated version of the difference. Okay? So there's a formula for transforming delta functions, which is very important in our case here. And I can write it in the following way. So if I have a delta function of 2 coordinates, let's say I go from y minus y prime, but I want to convert it to a coordinate in terms of, say, z instead, z minus z prime, and I give you the formula, okay, in terms of, if I give you the formula in terms of y in terms of z and y prime in terms of z prime, then what you will discover is that when you go from delta function in y to delta function in z, you will simply divide this guy by the Jacobian, the determinant of the Jacobian. So I'm going to write it in a symmetric way. So I will write this as square root of the determinant of y dy dz times the determinant of dy prime z prime. So these are Jacobians. Okay, these are Jacobians. Okay, and how do you remember that? Let me make sure I got that right. Actually, I wrote it in my notes, but I always forget the order of the. Yeah. So how do you remember this? Okay. How do you see that? So remember that dy of delta function of y minus y prime is 1. Okay, that's the simplest way to think about it. So when I change my coordinates from y to z, I can, right? So, but what multivariable calculus tells me is that I have to change my dy to dz, but I need to take the determinant of the Jacobian, dy dz. Okay? That's what this is about. Right? You calculate the Jacobian, which is a matrix, and then you take its determinant. This part is this part. And so if you want to still get 1, that means that you must have a delta function of what z minus z prime divided by the same guy, determinant of dy dz. Right? Because if you cancel these guys, then integrating over the delta function with respect to z will guarantee that you get 1. So that's how you remember the integration measure will transform like the Jacobian. And so the delta function must also transform like the Jacobian, but now the Jacobian appears in the denominator. But because it's a delta function, z must be equal to z prime. So I can write this guy in terms of the square root of this Jacobian times the square root of the Jacobian with respect to the prime coordinates. Okay, because, so in other words, I can symmetrize it because z equals to z prime. We're really talking about the same point because we're talking about a delta function. Okay, and that's where this guy comes from. Okay, and so all that talk about multivariable calculus is just for us to recognize that I need to divide. I can go to the next line, and this is now delta function of x minus x prime divided by the determinant of dy, in our case y is now r hat x divided by dx, and then square root, and then determinant of dr hat x prime dx prime, again square root. Okay? What does that mean? Let's do it systematically. So Jacobian of this guy is the following. It's actually, you take r hat a b x b. This is sort of my new coordinates, right? This is my y a, okay? And so dy a dx I, for example, is my I component of my Jacobian. But what is that? This is just dxi acting on r hat ab xb. These are constants, right? There's a bunch of sines and cosines and angles and so on, but it's constant with respect to x. So when I differentiate this, it just gives me r hat ai. Okay? Because it just differentiates x. So the Jacobian, and likewise for j prime ai, which is dy prime a dx prime y, this is just going to give you the same thing, r hat a I. So therefore, when I come over to take the determinant, or in other words, when I calculate r hat x inner product with r hat x prime, what you see is that you get delta function of x minus x prime divided by the determinant of nothing but because there's a square root, but both inside the square root, both of them are the determinant of the same matrix. So therefore, it's just divided by the determinant of r hat. But remember that rotations is defined by two conditions. One, the matrix is orthogonal. Two, the matrix has determinant 1. So this is in fact just 1, and therefore you get delta function of x minus x prime which of course is just the inner product of x, with x prime. Okay. And this is in fact a statement about rotational symmetry. Of space, right? So no matter how you rotate your bases, right? So you can think of this guy as the rotated basis of this guy, but no matter how you rotate your bases, they give you the same inner product, right? And inner product, remember, is the way we characterize distances in Hilbert space, and therefore the fact that it's independent of R, independent of the rotation, tells you something about rotational symmetry. But what does that tell you about D? Remember that this is also X, D, R hat, dagger, right? It's dagger because this is D, so when you take the dagger on both sides, then you get the R hat, X, is in fact X, D dagger, right? And that's why this is a D dagger, D R hat, X prime, and then if you compare it on the right hand side, this is now X identity X prime, and since X and X prime are completely arbitrary, we have derived the fact that rotation operators, the linear operator representations of rotations themselves, are necessarily unitary. Right, so again, rotation symmetry of space implies that the corresponding linear operators themselves are unitary. Okay? Any questions for me?
Sir,
Yeah.
why do you want to name the same thing to these? The determinants of particle one.
This one? Because there are 2 points, right? This is y and z. This is y prime and z prime.
But
There are 2 points.
they are not necessarily the same thing. Or
They are the same thing because of the delta function. But if you want to write it in terms of symmetric form, then you will split it into 2. But yes, they're the same point because of the delta function. Yeah. If you want to be a bit more strict about it, you can imagine a situation where I only transform one of the coordinates and not the other guy, right? Then you might only transform the one of the square roots. But again, it is the same thing. Yeah, but just different ways of writing it. Any other questions? No? All right. See you guys on Thursday.